Currently, unfortunately, more than 1 in 4 Americans suffers from a musculoskeletal condition or injury. And over half of the population in the developed world over the age of 50 suffers from a musculoskeletal condition. To have a device with the ability to directly track the motion of muscle would be very useful in the diagnosis and treatment of such conditions, and that it would allow for a direct quantification of progress during treatment. Unfortunately, currently available technology is not ideal for this purpose. Currently available technology includes Doppler ultrasound, electromyography, and gait analysis. Current Doppler ultrasound devices are generally wired, but both wired and portable devices are not ideal for dynamic studies. And they can be relatively expensive, ranging up to the tens of thousands of dollars. Electromyography measures the electrical activity of muscle and is therefore an indirect measurement of muscle movement. Gait analysis it gathers the inference of muscle movement, so it infers movement. It is also an indirect measurement of that movement, however, and it can be quite expensive, ranging up to the hundreds of thousands of dollars for equipment alone, not including the lab necessary to house that equipment. Here we can see an example of a gait analysis lab. The markers on the subject they're placed on the joints, and the movement of those markers is used to infer the movement of the muscle. Again, this is an indirect measurement. And we can also see in this photo that there is a lot of bulky, expensive equipment and a lot of space required. So it can be pretty expensive. So due to the shortcomings of current technology, we developed as the goal of our project to create a cost-effective wearable device that will allow us to have a quantification, a quantifiable, that would allow us to quantify the motion of muscle and to transmit data wirelessly in order to allow for dynamic studies. That being said, the requirements of our system would be to, in order to quantify the movement of muscle, calculate a velocity, the velocity of that movement. And the device, when worn, should not restrict movement of the muscle. Also, a wireless component should be able to transmit the data over a wireless protocol in order to allow for dynamic study. The functioning of our device relies heavily on the Doppler effect. And the Doppler effect is a phenomenon that occurs when wave energy, say sound for example, traveling from a source, undergoes a perceived change in frequency and wavelength dependent on the movement of that source relative to an observer. And you can use the information from the frequency shift to calculate the velocity of the source. So in this image, we see a transducer that acts as both a transmitter and a receiver. As it transmits the wave energy, the sound, the waves, to the muscle reflects the waves and then acts as a secondary source. We can then use the information and the wave, including the Doppler frequency shift, to calculate the velocity of the muscle. This can be transferred to 2D and 3D. So if you have multiple transceivers, you can create a multidimensional velocity vector, which are more accurate depictions of the velocity of the muscle.
As our design approach, since the waves we are receiving in the transducer are modulated, we built a demodular circuit that will give us our frequency shifts we are trying to record. We also designed the cup that will hold the transducer in place. Use the microcontroller to sample the data and transmit the data wirelessly, and use MATLAB for signal processing. One of the challenges we overcome is that this is a feasibility test. There is no device like this in the market, and we are using a fetal heart rate monitor as our continuous wave probe to measure muscular movement. So as I said, the wave that is received by a transducer is modulated, so demodulation needs to occur in order to get our frequency shifts. More specifically, we will be demodulating with the carrier we transmit to get a positive and negative frequency shift and record a positive and negative velocity. The demodulation we are using is IQ demodulation, quadrature-based demodulation, which receives the modulated signals and mixes them with the carrier signal and a 90-degree phase shift version of the carrier signal to give us our in-phase and quadrature phase values after they have been passed through low-pass filter to remove any unwanted frequencies. This is our components for our IQ demodulator, which has a low noise pre-amplifier that gets the single-ended signal, the modulated signal, and turns it into a differential signal that is passed to our demodulator, which performs IQ demodulator along with a 32 megahertz signal. The reason being, we're using 32 is we're divided by 4 to get our carrier signal and a 90-degree phase shifted of our carrier signal. This is then passed to our transpedance amplifiers, turning the currents from the demodulator to a voltage, and acting as a filter as well to get our I and Q value. So this is a circuit diagram for a single IQ demodulator. This can be increased depending on the number of probes we use. To the top left, you can see the differential amplifier. To the middle, you can see the demodulator, and then at the right, you can see the transpedance amplifiers to give us our I and Q values. This is the top level of our design. We see the 8 megahertz ultrasound probe being emitted, modulated signal being received by the transducer, passed to our quadrature phase demodulator, which gives us our I and Q values, which are then sampled by our microcontroller, transmitted wireless, received by our second microcontroller, and passed to the computer to do some signal processing. More in depth, you see that the modulated signals are passed to the low noise preamplifier, passing on the differential signals to the demodulator along with the 32 megahertz oscillator, and then that is sampled by the microcontroller, transmitted wireless by our microcontroller. Second microcontroller receives, communicates serially to our computer, transmitting the data so we can get our spectrum. The microcontroller we are using allows us to use the Zigbee wireless protocol on board up to with a transfer rate up to 2 megabits per second, sample up to 330 kilosamples per second, and communicate serially up to 2 megabits per second. For the design of the cup, we wanted to design a holder that would allow us to move the transducer at different angles. As you can see to the right, we designed an arbitrary style holder that as the inner circle can move freely at different angles as the outer one is held down. And you can see an example of that on the picture to the left. This is the design of our final circuit diagram. You see the transducers at the bottom right with our microcontroller under our demodulator circuit.
So to ensure that our demodulator circuit is functioning properly, we use signals from the function generator for unit testing. So we used a 2 megahertz local oscillator signal, as well as a 505 kilohertz and a 495 kilohertz inputs, which emulate a modulated carrier signal of 500 kilohertz. So what we saw at the output were I and Q waves, which were phase shifted by 90 degrees. And when we added the I plus J times Q of these two signals, what we received was a complex message signal, which contained both frequency and phase effect. So when we passed in an input of 505 kilohertz, we saw an output of positive 5 kilohertz. And when we passed the 495 kilohertz, we saw an output of negative 5 kilohertz. The experimentation of the wireless transmission unit was done by measuring the average, or the total number of bytes sent versus the total bytes received. And what we saw was that as the distance was increased, the error rate also increased. So you can see that after about 6 feet, the error rate jumps to about 35%. And because of this effect, we had to limit all of our testing to maximum range of about 1. So Here you can see the unit testing of our probe, which was done on the string phantom setup. So the string phantom is a motor-driven string which moves the string at a constant velocity. And the string can also be submerged in different mediums, such as water. We chose to do our testing in water because the speed of sound in water is approximately the same as the speed of sound in muscle. So when looking at a spectrogram of our measured frequencies, we can see the Doppler shift. The average frequency of the measured Doppler shift is indicated by the white line. To see how this compares with a theoretical Doppler shift, see that it's very close, and that's indicated by the black dotted line. So for this trial, the string speed was 15 centimeters per second, and the Doppler angle was 70 degrees. When we used an instantaneous reversal, when we introduced an instantaneous reversal in the string velocity, we saw that we were also able to see a shift in the measured Doppler, in the average frequency of the measured Doppler shift. So this allowed us to calculate velocity in both positive and negative directions. We also took recordings from the muscle group, specifically the forearm muscle or brachioradialis. And when we flexed their fingers, we saw that there was a positive shift in the frequency. And when we extended it, we saw a negative shift in the frequency. Here you can see Jason with the probe on his forearm. And what you're looking at is a real-time FFT of the output of our demodulator circuit. So you can see that at around 700 hertz, there's a Doppler shift. It's a bit hard to see, but you can see both positive and negative. So this is a video of our string phantom setup of the entire circuit. So the output of the probe is being fed into our demodulator circuit, which is being sampled by the microcontroller. The microcontroller then transfers the data wirelessly to a receiving microcontroller. This microcontroller is connected to the computer via a USART serial interface. So this is hooked up directly to MATLAB, and the data is read in. So after some filtering, we can see that spectrogram. So the conclusion of our results were that, as in both the reverse and forward tests, as the speed of the string phantom was increased, the error also increased. And you can see how our average measured Doppler shift compares with the calculated or theoretical Doppler shifts.
Due to the mismatch between the 8 megahertz carrier signal from the probe and the 8 megahertz frequency derived from a 32 megahertz crystal oscillator, we saw some unwanted residual frequency. We tried mixing the two frequencies together, and we were expecting to see a DC signal, but instead we saw a sinusoidal signal, as you can see in the screenshot. Now the residual frequency did initially show up in our spectrogram analysis, but we were able to filter it out through signal processing. For future revisions, we can add multiple probes to add more dimensions to the velocity vector study. An SD card can be implemented into the microcontroller part, so it can actually save the data before wireless transmission. That way, even if there's some data loss through the wireless transmission, the original data can always be secured. Also, a full PCB design can be implemented to provide more portability and to make the design more compact. Also, the background noise of the probes can be recorded, and it can be subtracted from the spectrogram received from the probe. That way it gets canceled out the noise and increase the accuracy. So more reliable and higher range for wireless protocol can be used because from the experimentation we saw that our range wasn't greater than 5 feet, but we would, in future experimentation that can be. Right here, this is the hours spent by each of our members during this semester, followed by the funds spent in effort to build a prototype. This is a summary of individual contributions. Jason was our project manager, I was our technical manager, Brittney was a software manager, and I was the financial and hardware manager. Our project involved the integration of several different engineering principles. So we learned a great deal from this project. Starting with, we learned how to use Doppler effect to calculate muscle velocities. We also learned about several modulation and demodulation schemes. Also, we learned about signal processing in MATLAB, and moreover, we learned about system integration. We would like to give a special thanks to our faculty advisor, Dr. Sekar, and also Dr. Economy and Dr. Pankrazia for their advice. Thank you.